Hi everybody, welcome to the talk Overcoming GIL with subinterpreters and immutability with Yury. The stage is yours.
Hi, everybody. My name is Yury Selivanov. What you see behind me is one single Python process running 10 async I/O event loops, saturating 10 CPU cores on my laptop. That's as many as it has, all sharing one mapping between them, exchanging values between them, Python objects. Um, and the mapping itself has 1 million keys and values between them, all done fairly efficiently. So how do you build something like this yourself? Let's say you want to build a fast Python service. How do you do that? I think I see some people leaving. We're going to be building fast things with Python. It's possible. So what are the options? You can do single process. You can run async I/O. You can put UV loop there. You can do some serious processing. You can do a lot of requests per second this way. But I mean, if you have a 64-core server CPU, this will make it sad. So what are the other options? Well, we can go with multiprocessing. This is battle-tested, industry-standard way of how you do things like this. This is fine. We can draw pretty diagrams like this. You have your mighty database that can store the state, and you can run all those Python processes, as many of them as you want. This is all beautiful, except we are not living in a diagram universe. We live in a universe with like speed light limit and whatnot. So this diagram is wrong. So which one is the correct one? This one is the correct one. This is latency. This is the mother of all problems. And if this doesn't look serious enough to you, this is the industry accepted way of visualizing the difference between memory access and network. Network is always fast. It's always depressing. It's always full of surprises. So if you can avoid network, do that. So we're back to square one. What are the options? Well, maybe you can use threads. If you have Galaxy Brain, if you know how to control threads, if you know how to write thread-safe code, maybe you can do that, except in Python we have GIL. And I guess we can talk about GIL a little bit. And I'm curious, how many of you in this room actually want GIL to go? Okay, maybe I'm in the wrong room. Because I actually kind of like GIL. Every time I myself doing like free threads and multi-threaded programming, like this happens to me. It's just ridiculous. The complexity of multi-threaded programming is absolutely ridiculous. Everything can go wrong, and I want to hold to something familiar like GIL just to get myself out of this horror. Multi-threaded programming is really hard. So we're again back to square one. Even if we wanted to use threads, we really can't. Although Python core team is working on no GIL, it will be shipping a version of Python without GIL. We'll be shipping really soon. But it will likely take a couple of years at least to stabilize it, to make sure that all the packages on PyPI are compatible with it, or more. So what do we do now? Well, maybe we can use this new, relatively new thing in Python, subinterpreters. And what's new about them specifically is that now you can actually run Python subinterpreters side by side, and each one of them has its own GIL. But they run completely isolated from each other, completely independent. They cannot exchange any information between them, except some very primitive information. But this actually gives you parallelism. You can run a bunch of them in the same process, and each one of them will occupy one of the CPU cores. This is beautiful. And what's actually even more beautiful about all of this is that they all ultimately share the same memory space. And this is very important, and we'll get back to this slide later. So with all of this in mind, we can sort of start outlining our architecture. We want to build a service, so probably one of the subinterpreters is going to be the main one, and it will spawn several workers, and perhaps we can have queues between those workers to sort of distribute our tasks and communicate between them. This is pretty cool, except you would have to use pickling. You would have to pickle objects to send them to subinterpreters. And pickle is slow. So, what are the options? Well, what if there was a way to avoid pickling things? And what if there was a way to actually have safe shared state, and potentially lots of it, so that all those subinterpreters can access it very efficiently? So we're about to talk about efficient data sharing, about isolated subinterpreters. And I built a little library for this. It's called MemHive. And I will give you a quick overview of what it can do. This is a very simple snippet of code, and I will zoom in a second. But an important thing about MemHive is that its architecture basically has 3 levels. Level 1 is very simple, just a couple of functions protocol that allows you to send Python data across the subinterpreter boundary. Level 2 is more high-level API that adds queues and synchronization primitives. And level 3 is the async IO bridge. And we can talk about this async IO bridge a little bit. So here we create MemHive, and then we define the actual asynchronous worker that we're going to be running in every separate subinterpreter that will each have its own async IO loop. Here we can access some shared state. We can listen on messages. We can send them. And here we're actually spawning those worker subinterpreters. We're going to be spawning 10 of them here. So this is fairly simple. And then this is the main subinterpreter in which we can initialize this shared state. We can broadcast signals to all subinterpreters, or we can push some work so that one of them starts working on the task. And then we can also listen on the messages. So this is fairly simple. And actually, I guess I could have given a talk to you about this API, explains how it works, how to build with it, and all of that stuff. But I think the API itself is fairly minimal. It would probably take you a few minutes or like a couple of tens of minutes to figure out how it works. So instead, what I think we should talk about is how this all is implemented, so that you don't think that this is some witchcraft magic that nobody understands. I want you to understand how this actually works so that this doesn't happen to you when you use it. All right, we have 3 things to talk about on this talk. One is immutability. The other is how to do immutability efficiently, and then how we can profit from it. So let's start with the first one, immutability. So Python actually has a few immutable data types, like strings, integers, floats, bytes. It also has tuples. And with immutability, it's pretty easy to use. So we have our string we want to capitalize, and this is what we do, right? Well, no, it will not work. So what we have to do, we have to sort of create a new object out of an existing object. This is what happens behind the scenes. This is fairly intuitive in Python, so we're not thinking about it much. But you cannot mutate strings in Python. Same about tuples. Tuple is this kind of nifty data structure that we use to represent records in Python. It's unlikely that you would be storing millions of elements in them. You usually store things like, I don't know, X, Y, and Z. And here, to actually, let's say, mutate tuple, we are not mutating it itself. We are creating a new one. But you probably noticed that there is no immutable dictionary or immutable mapping in CPython. And it's a shame, because it would be nice to have it. So let's just imagine how it would look like. Well, probably similar to strings and tuples. So you can create it. You can initialize it with, I don't know, dictionary or key value pairs. And then, if you want to add stuff to it, you essentially call a method on it, and it will give you a new collection. And this is exact one-to-one mapping to what we have with tuples, what we have with strings, and all other immutable types in CPython. So this is pretty easy. We just covered immutability. We now know pretty much everything about it. Now let's talk about how we do it efficiently. So when we do this, and by the way, we are about to hit peak computer science in this talk. So once we are past this thing, everything's going to be easy. So what is the complexity of this operation? If we can use the big O notation, this is ON. So basically, it's proportional to the number of elements in the tuple. Like this whole cloning thing, we have to create a new one, then we have to copy those elements one by one. It's ON. So this would be really bad if we had ON complexity for the similar operation on the mapping, on the immutable mapping. And the reason for that is that we're using tuples differently. Again, we're using them for small records. But what about dicts or maps Well, we can potentially put millions of elements in them. We can potentially use them as cache. So if adding a cache entry requires us to rebuild the whole thing every time, that's going to be unacceptably slow. We cannot do this. Fortunately for us, there are smart people who figured out nice algorithms with which we can implement the complexity of these mutation operations with O log n complexity, which is really, really good because log grows significantly slower than the ON function. So if we butcher the big O notation a little bit, we can even say that it's O log 32n, which is even better in use. This grows even slower. Or, I mean, if we're willy-nilly about it, we can even say that it's O1. If the collection is small enough, like a couple of tens of thousands of elements, this is going to be fairly quick. Or if you can just say that the complexity of this is doesn't matter. It's going to be fast. So now let's try to actually understand how this stuff works. So let's start by creating a collection, and I will explain you what actually happens on the background. So the trick to this data structure is that it uses trees behind the scenes. As an engineer who uses this mapping, you have no idea that it uses trees, but it does on the background. You never interact with it directly, but this is what's happening on the background. So here we have an empty collection with an empty root node of this tree. There is nothing in it yet. So let's start putting some elements in it. So we're adding key A that is set to value 1. We do some computation, basically to determine where exactly we should put this key value in our root node. And then we do the same for B, and then we do the same for C. And then something else will happen because we're about to add a key that has like a little conflict. So essentially here we have to branch our tree. So we create another node and we move our C thing to another level of this tree. And then we can keep adding stuff. So as you can imagine, this tree will grow as your collection grows. So as you keep pushing things, this tree will become bigger and bigger and bigger and bigger. So why is this actually cool? Imagine that now we want to mutate this thing. Like we want to create a new mapping with one more extra key. What do? Well, we run our algorithm. Like here we want to insert key H. We run our algorithm. We determine where we actually want to put this key. And then we have to copy this root node. Remember, the data structure is immutable, so we can't mutate it. So we copy that root node, put our H key in it. It's now there. It's fine. And here where the magic happens. The magic happens here because we don't have to copy the second level of this tree. It's fine. It's fine as is. We just need to reference it. We can reuse most of this tree. We don't have to do anything to it. It's the same. So this is the magic behind this efficient data structure. Because you can imagine a mapping with billions of keys in it, you add an element to it, and only 5 nodes out of, I don't know, 10,000 changed. So this is why it's so efficient. So this is called structured sharing. And this is what will help us a lot with our subinterpreter magic. The actual algorithm is called HAMT, which stands for Hashed Array Mapped Trace. I actually implemented this data structure for Python. It's in Python standard library, but it's kind of hidden. It's used to make the context vars module work. But if you're curious about how this algorithm works and want to check out the code, hmt.c file in Python repo is the best place to see it. And also it has this giant 200 lines long comment that explains how the data structure works in very deep detail. It's a fascinating data structure. There's a lot more to cover in how it's implemented, so I recommend you to take a look if you're interested. Anyway, we just covered efficient immutability. Now let's get back to how we can actually use it. So remember, all subinterpreters run in the same OS process, which means that they all share the same memory space. So imagine that we have our main subinterpreter on the left, and we have one of the worker subinterpreters, a separate Python interpreter, on the right. And we want to access this collection from the main subinterpreter. So what we can actually do, we can just look into the memory of that collection directly We don't need to copy the whole thing. It can stay. It can stay in the main subinterpreter. Because it's immutable, we know that it will not change. So it stays in place. So it means that we can access it. We don't need to capture locks. We're not going to have any lock contention or anything. It will just work. And this is basically how it works. So we start looking up a key. We ultimately get routed to the main subinterpreter, and we find it. What's even more mind-blowing and fascinating about this all is that with this, you can actually have efficient mutation. So like in this case, for example, just like what we just discussed before, if you want to add a key, you don't have to copy the entire tree. You can just create the missing new branches and reference the others. So if you have a collection with billions of keys and you want to add a new one, you will just create a couple of those underlying, under the hood, tree nodes in your worker subinterpreter, and the rest can be reused. You don't have to do anything about it. And the beauty of it is that when you pass this mutated mapping back to the main subinterpreter, you only need to copy those 3 nodes or 4 nodes or however many you have, but it's surely going to be less than the entire collection that you are just mutating and shared. So it's basically the key point of the key idea of all of that. Because we're using immutable things, we can actually access the underlying memory safely without acquiring locks or anything. We do have to do a few nifty tricks here and there, like for example, you're accessing an int value. We basically have to lazily create a matching int value in the subinterpreter for you, because you cannot share Python objects. But memcopy is what we have to do here, is extremely fast. It's like one of the most optimized functions in the C standard library. So the overhead of that is really, really low. So MemHive now implements this mapping structure. It can also implement lists in the future. There is a similar algorithm for representing lists, which with very efficient append, prepend, indexing operations, also log n, if I recall correctly. And once it has lists, then you will be able to share lists of, again, millions of keys effortlessly between subinterpreters. And basically, as I explained before, we copy on access or like lazily things like tuples, ints, strings, and bytes. But again, this is very, very fast operation. So now let's try to benchmark this somehow. So in the main subinterpreter, we create this collection, very simple one, mapping with 1 million key value pairs. We want to pass it to one of our workers, and then we want to mutate a number of keys, like add a few or maybe update a few. So this will cause all this sort of tree juggling in the background. And then we want to pass it back. And it's like this bottom thing that we want to benchmark. We can either pickle, unpickle it, like this is one option. This is how we do it now. Or we can use all of this structured sharing magic to do this transfer. And when we benchmark it, you will see that there is green line, which is pickle, and then the blue line at the 0 axis. And this is the useless chart of them all. It's completely unusable. The interesting thing to note here is the pickle line. Pickle pretty much stays consistent because it doesn't care. Like you have a mapping with 1 million key values, you add 100 or 10 to them, it's practically the same thing. The overhead is still going to be the same because it still has to sort of iterate through all of them, pack all of them, and do all of this stuff. So this line is constant. Let's just get rid of it. And if we do, then we'll see that passing this collection with millions of keys back with just a few modifications is a sub-millisecond thing. It's fairly quick. So now you might ask me, Yury, what about smaller collections? For smaller collections, pickle might actually be faster. Sure, let's do it with just 10 key value pairs. And we have to switch our y-axis to nanoseconds here to see anything. And you can see that the structured sharing still wins. It's still significantly faster to do structured sharing instead of using pickle. Even when we are rewriting the whole collection, even if we are modifying everything, so our tree is a new tree essentially on the background, and we have to copy the whole thing, copying is still faster than going through all of the overhead of Pickle. And I had big doubts about this chart, and some prominent, very prominent Python core developers told me that people will not like it, but I still want to have it, even though when I myself see something like this, I get immediately triggered, like this cannot be true. But this is the speed up that you can get with using this system, and it's a true one. So it obviously depends on how many modifications you make to your shared data structure, how much of it you actually update. But this is the true range. If you update all of it, well, it's going to be 6 times faster than Pickle. If you update just one key, it can be this ridiculous number times faster. There's a lot of interesting implementation details here that I would love to chat about, from the design of the actual data structure, how it's implemented, to how we can actually guarantee the safety of this data sharing mechanism. I had to create a concept of like remote incraffing and decraffing, and incraffing is something that sort of keeps Python objects alive. When the reference count number goes to 0, the object disappears. So we cannot afford an object disappearing in the main subinterpreter while we are reading from its memory from another subinterpreter. There's a lot of interesting details of how this is actually built and designed to avoid lock contention, to make it really efficient and avoid nasty things like deadlocking. But we don't have time for this. It's a separate talk. I'll probably make a YouTube video or write a blog post about this, so stay tuned. Now, is it open source? Well, kinda. I mean, I opened the repo yesterday. It's on GitHub. I wouldn't call it open source. It has Apache 2 license, but open source means more to me than just giving you the source. It means that I would merge your pull requests or answer to your issues, or that it's stable or that it's usable. Unfortunately, it's not. It's still sort of a prototype. It implements the hardest part of it all, but still a few bugs here and there need to be fixed. And a few new APIs have to be added. And for the bravest of you, I even added a README file that says, do not use in production or you will be fired. And I believe that's true, because it will not work. Don't use it in production just yet. But I'm building this thing for HDB, which is my company, which is a database that has a fairly big Python component in it. And we need to have this thing to optimize our cloud deployment. So we're going to be working on it. We're going to be integrating it. We're going to be dogfooding this stuff to ourselves to make sure that it works. Anyway, my name is Yury Selivanov. Follow me on Twitter and GitHub. This is MemHive. Thank you.
Yeah, thank you for your talk. The question is maybe just a very practical question. What is the most common task that would benefit from switching from async or multi-process approach to sub-interpreters?
The most simple thing, in my opinion, would be running multiple async I/O programs side by side, all sharing cache between them, for example. That would speed up your web application. Or, for example, if you have an application that has to do computation, let's say do some NumPy number crunching, then you can have a few subinterpreters doing just that, and a few async I/O processes doing the I/O, accepting the requests, and dispatching those long calls to those subinterpreters so that they don't block and things keep running fast.
Hi. So when you iterate over the dictionary or you do a lookup, you have to dereference a lot of pointers, actually.
Yes.
And that creates a lot of cache misses. Do you have any metrics on that already?
I did benchmark it. Obviously, recreating sort of all of those little objects is costly. It's not prohibitively costly. It's like going to be 30% slower than if you do it in the main subinterpreter, but it's not prohibitively costly. It's not like a 10x increase. Again, memcopy is really, really, really fast. So I can pay this 30% increase in cost of iteration. And potentially, as this thing grows, it's possible to implement interesting optimizations on top.
That's the mapping. You said you're going to produce a list. Is that something you need, so you will be doing it, or is it just a nice? It would be nice to have.
We might need it. It's hard to know right now if we need it or not. The data structure itself, like the source of the implementation to look at that I would use would be Clojure programming language. This is actually the source, was the source for this HMT implementation. I basically had Java code on the right, and I was writing C code on the left. So they also have this data structure for lists implemented. I would just go through it. If I don't do it, somebody else can do it. It would take about a week of programming, but it's very doable. It's not something that will take years.
Hi. So a common gotcha with like tuples is that tuple is an immutable data structure of potentially mutable objects.
Yes.
How does that work if you share like a tuple or other structure sharing with subinterpreters if you mutate the underlying objects?
This is an excellent question. So right now it will just error out. Like it will not allow you to share mutable collections. So you can have a tuple with let's say elements 1, 2, and 3, and then a list. You will be able to access elements 1, 2, and 3, but on the list it will just tell you, I'm sorry, I just can't. But my plan with this is, I'm not sure yet. Like either we're gonna keep this runtime error, or we just gonna create a tuple equivalent in MemHive, and then basically we will only allow you to either store atomic scalar things in this data structure and our approved data structures that will not allow anything else but approved data structure in them recursively, or just stick with the status quo and basically just error out. But it will not allow you to share mutable containers or any immutable state in it. It has to be all immutable.
Thank you for your talk. And actually, the previous question was the same one I had, but I have a follow-up. Do you think it would be possible to perhaps, tag certain objects as becoming immutable at a certain point in their lifetime, and so then they wouldn't have to be copied between subinterpreters?
The answer to this question, surprisingly, is yes. So this HMT collection thing has an interesting API that is called mutation API. So essentially, you can say, hey, I'm going to be mutating this tree for some time now. So don't do this like cloning of nodes every time I'm doing it. Just write directly to them. And this is actually implemented for support efficient unpickling or efficient updates of the tree when you want to atomically update the tree. It's implemented safely inside. Like there's some magic that sort of enables safe mutation. So that other things that reference the same collection will not see that mutation happening. But it's possible. So what potentially we can do with this, you can create an immutable mapping. You can start the mutation thing going, and then it would act like a dict, basically. You can mutate around. And when it's done, when you're satisfied, you freeze it, and then you can share it.
Thank you.
Hi. I'm wondering about your benchmarks. It looked like you accessed like the first 100 indexes for mutation, which seems like they'd be likely to be part of the same branch of the tree. What would happen if those mutated indices were randomized over the entire range of your mapping?
Oh, that's also a good question. That said, I've ran this benchmark multiple times, and the hash randomization kicks in Python, so it's actually not in the same route or in the same path. Every time you run benchmark, it will affect different branches of the tree. But honestly, it doesn't matter much. If you have a collection with 1 million items, the tree behind it is going to be very diverse. So one way or another, you're probably going to be mutating the same number of branches. It really doesn't matter. All right. Thank you very much.